Hey, what up? How's it going? Can you guys hear me?
Good, you?
All right. We'll give everybody a minute to trickle in, and then we'll get started with what we're talking about today. Also, did it rain where you guys live?
Yeah, it's raining right now.
Yeah, it's raining right now.
Same. I'm very excited to go for a run in a bit. There's almost never anybody out there while it's raining. I'll probably head out right before lunch and get my run done. Also, look, it's a cat. Look at that catto. Ooh, stop moving, don't shake. Okay, that'll stop shaking in a second. Okay. For today's warm-up, I got two parts for you. One of them pretty straightforward, the other one pretty hard. So item number one here, I would like you to calculate the perimeter of this wedge. And here are the two pieces of information that I'm giving you guys to figure this out. Piece of information number one, the angle that is being measured from the center of the circle of this arc is 70 degrees. And if one could measure the circumference of this entire circle, that circumference would be 14 meters. So for this wedge, knowing that it's a wedge of a perfect circle, calculate the perimeter, which is to say a little bit of vocab all the way back from chapter 1. What is the length all the way around this wedge? And then item number 2 over here, a much more difficult question. This one, if you get even close, that'll be impressive in my opinion. Show that the arc length S must always be greater than the chord length D, right? And notice what's similar about D and S here. They share what measurement?
Theta.
They have the same arc measurement, right? They're both formed by that same angle with the middle of the circle. So come up with an equation for both the arc length S and for the chord length D. And if you are clever, we should be able to show by the comparison of those two equations that no matter what, D has to be shorter than S. And I mean, the big hint here is this is actually a law of cosines question. Do your best here, and technically you don't have the information for this, but there are statements that we can make about cosine that are comprehensible that will show that this second statement must be true. Is that okay? Any questions out there about the warm-ups?
No.
Okay.
Oh, actually, for the perimeter one, can we round the decimals, or do you want us to have like an exact answer?
Give it in fractions of pi.
Okay.
Yeah, leave it exact. And also, you'll probably notice if you pay attention to the backgrounds or whatever, I'm not in the same room as I normally am. Today I'm downstairs in the kitchen because since we're out past the AP test, today I taught AP Physics how to make coffee. If you want to see a replay of that coffee making tutorial, that'll be on my YouTube channel that I keep all the other classes on, except I'm sure normally when you guys on there, you just go straight to the Geometry Honors playlist. If you want to see the coffee video, that'll be under the AP Physics 1 playlist in case you want to check that out. Just delicious coffee. Delicious cup of hot coffee on a rainy day. Anyway, I'm going to give you guys a minute or two to work on this. In the meantime, I'm going to clean up a little bit of the junk in my kitchen. I made a little bit of a mess making coffee, so I just have a couple things to move around. Oh, also, have you guys watched any of those YouTube videos out there about making sourdough? Like making your own bread at home?
Oh yeah, my dad watched that. I think he's gonna do it.
Oh my God, yes, I'm making sourdough right now and it's so good. It takes 3 days, but at the end of those 3 days, you have delicious bread. Do you guys want to see my sourdough stuff?
Yeah.
Yeah, so here's my sourdough starter. It looks gross because it kind of is. It's just yeast that you keep growing in the bottom of a container of water and flour. And once a week, I move 2 tablespoons of this guy to another cup and refresh it. And then this is enough starter in here to make 2 entire loaves of bread. So I've been making 2 loaves of bread a week. Yeah, it smells like a bakery. And then since I make 2 loaves, wait, can you guys still hear me?
Yeah.
Okay. Since I've been making 2 loaves of bread a week, right now I have 1 loaf ready to go in the oven. I'm going to bake this right after we're done with class. I might even preheat the oven before this class is over. And you like leave it in the fridge overnight, turn it over in a basket. So this is like the next loaf of sourdough that I'm going to bake today. And that sourdough loaf will be a replacement for the one that I just finished. But yeah, go and check out the results. So this is my like bread box. I really like baking bread. It's got a good flavor to it. It's been really good with avocado. But yeah, baking's fun. You should absolutely give it a try. I would also check out the Bon Appetit sourdough video. They have all the information that you need about technique in that video that you could ever want. Anyway, item number 1, let's go ahead and calculate the perimeter. So how do we start this one off? What are we actually being asked to do here?
All you have to do is find the arc measurement, and then after that, you just have to find the radii and add them up together.
I would say the big thing is, the thing we need first is the radius, and that's because not only do we need to consider 2 times the radius in our calculation, but also the fact that you need the radius in order to calculate the arc length, which is what's on the outside there. So if the circumference is 14, this means that 14, oh no, my pen. Oh no, it's fine. 14 is equal to 2 pi r. And so what is our radius r?
14 over 2 pi.
Yeah, I could divide both sides by 2 pi, divide both sides by 2 pi. 2 pi and 2 pi cancel. And what's 14 divided by 2?
7.
So 7 divided by pi meters is approximately equal to our radius. And so that is to say that, you know, it's 7 divided by a number which is a little bit more than 3. So this radius should be just a little bit more than 2. Is that okay?
Yeah.
Okay. And so for this diagram, this is a radial length, this is a radial length, and then out here, this is the arc measurement, or sorry, arc length, which we normally call S. And so the arc length S is going to be equal to, what is just the pure arc length equation with nothing plugged in?
What is it? The angle times pi times r divided by 180?
It's arc measurement over 360 times circumference, or theta times pi times r.
Right, so that both of those equations that I was just given are identical. So this is typically the way that you want to use it. It's just going to be theta divided by 180 times pi times r. But where this comes from logically is the derivation. And that is to say that it's the same as theta divided by 360, because this is asking the question, what fraction of the circle do you want the circumference of? Then multiplied by the circumference itself, 2 pi r. But we normally write it this way because this has 2 constants in it, the 2 and the 360, which can simplify down to just 180. But both of these are perfectly good statements for arc length. Usually I use this one just because it's a little bit easier to remember, but if you're gonna have it already written down somewhere, this one's already simplified. Nonetheless, we take and we plug in our two values, and so that arc length out there is going to be equal to 70 over 180 times pi times the radius, where our radius is 7 divided by pi. So pi and pi cancel, and so do these zeros. So that is to say that this is going to be 7 times 7 divided by 18. And so what is our arc length measurement?
49 over 18.
Yeah, 49 divided by 18 meters. So this is to say that our total perimeter is going to be equal to that arc length on the outside of the wedge plus one of the radii plus another one of the radii, because to go all the way around, we need to first travel S, and then R, and that will get us back to where we started. And so our final answer is going to be equal to 49 over 18 plus 14 over pi meters. And if you want to take that and turn it into a common fraction, you could. Probably not very good use of your energy.
Mr.
That'll probably take a bunch of work and not return that much of a benefit to you. Yes?
Wait, would it be 14 over 2 pi?
No, if you multiply a fraction by 2, you multiply the numerator, not the denominator. So it would be 14 over pi.
Oh, okay.
Yeah, 14 over 2 pi would simplify back down to 7 over pi, and then that's only one radial length. This is 2 times the radius. Is that okay?
Yeah.
Okay. So that's item number 1 there, the perimeter of a wedge. And now item number 2, this circle. We want to try and show in common terms that literally no matter what numbers you use, S has to be bigger than D, right? We have a tenet from Euclidean geometry that says the shortest distance between any 2 points is a
Line.
perfectly straight line, right? And so that's not just like a topic that we ask you to memorize, and it's not just a thing that makes sense. If it's actually a true mathematical fact, you should be able to show that by using equations in any context where that would be a valid statement. And this is a valid place where we can try and make those types of statements. So if a short line is indeed the shortest path between any 2 points, then no matter what number theta is, that length D should always be shorter than that length S. And let's go ahead and do that by setting some common variables here. Now we have theta, the angle that it makes in the middle, but what other thing are we going to need to define here so that we can compare S and D? What length do you think we're going to use as a standard? Yeah?
Radius?
Yep. So we'll be able to do this because both of the lengths here on the left and the right are the same length. They are both just the radius. So first, let's go ahead and define S. I think S is going to be the easier one to define here. So what is S equal to?
It equals the angle times...
Theta over 360
Yeah.
times circumference. Also 2 pi r. So then it would just round down to the thing that we did before.
Yeah, I would simplify down, though this is still a precise way to state the arc length. So this is to say that the arc length S has to be equal to theta divided by 180 times pi times r. And if we got crazy, we could like try and come up with some sort of common value of pi over 180. So 3 divided by about 180 would be about 60-ish in the denominator. We could work it out if we wanted, but this is saying that if you want that arc length, you're going to take theta, you're going to multiply it by the radius, and then divide by about 60. So now let's go ahead and come up with an equation for D, and the big hint here is the law of cosines. So D squared is going to be equal to what?
R squared plus R. What is that?
R squared plus R squared minus?
Yeah. Plus minus 2 times R times R.
So minus 4r.
Yeah. And then
Times
cosine of the
cosine
angle theta.
of the angle theta. So in case you're having a hard time seeing it, this down here is just the law of cosines, but for this triangle right here, where the reason why we're using the law of cosines is that number one, it's oblique. I'm sorry, it's, yeah, no, that's the word I want. Yeah, it's oblique. It's not necessarily a right triangle. And we're being given a side, this inside angle, and then another side. And we're being asked to calculate this over here. So when we're given SAS or SSS, the only way to proceed with calculations for that triangle is the law of cosines. So yeah, now we can take this here and we can solve this for D. So then this is going to be, D is going to be equal to the square root of, D is going to be equal to the square root of 2r squared minus 2r squared. So this is r squared plus r squared. This right here is just going to simplify to 2r squared. And then minus 2 times r times r. Well, r times r is r squared. And then this 2 just comes from the law of cosines. So on the inside here, it's going to be 2r squared times cosine theta. Is that okay for this?
Yeah.
What can I factor out here?
The r and the 2r squared.
2r squared.
I can factor out 2r squared. So this d is going to be equal to the square root of quantity to r squared. And then if I factor out 2r squared from these two terms, what's left behind? What happens if I factor out? If I factor out 2r squared from 2r squared, all that's going to be left is 1. And then that's going to be minus, what's this, if I factor out 2r squared from it?
Cosine theta.
Yep, so that there's just a little bit of factoring. And now I'm going to pull out the 2r squared from the inside here to the outside of the square root. So that is to say that that chord length, d on the outside, is going to be equal to square root of 2 times r times the square root of 1 minus cosine theta. Is this okay?
Yeah.
So I have a statement for S, I have a statement for D. Both of these are in common variables. They're both written in terms of the radius of the circle r, the angle theta, and some other functions or constants. So if what I'm saying is true, then if we want to establish that forever the straight line path must be shorter than the arc length, then I can write these two together in the following inequality. Well, if this stuff is true, if geometry is not a lie, this length must always be shorter than this length. So I can make that statement about these equations. The straight line path, which is going to be root 2 times r times the square root of 1 minus cosine theta, this number should always, always, always be less than theta over 180 times pi times r. Is that okay?
Yeah.
So all I've done is based on this initial statement here that we're trying to prove, say that the straight length d is less than the arc length s. The straight length d, the chord length, is less than the arc length s. What can I divide out of both sides?
The r and the theta? No, yeah, just the r.
Just the r. So the theta is trapped inside of the cosine, and further, this cosine is trapped inside of the square root, but both of these r's are on the outside and they're both singular. I can cross those out. And so here is kind of the final stage of our comparison. Square root 2 times square root 1 minus cosine theta. This must always be less than theta divided by 180 times pi. I'm going to have to leave it here because to take this any further would require pre-calculus. But I think here are some interesting features about this derivation. The r cancels out. which means that this comparison, it doesn't depend on how big or how small the circle is whatsoever. This relationship will hold true. So that is to say that no matter how big or how small your circle is, every chord length will always be shorter than any given arc length. To go past here, you guys would need a little bit more math so that you could relate cosine theta in some intelligent ways. But I challenge you, no matter what number you choose for theta, it doesn't matter what number you choose for theta. Any number from 0 to 360, it just has to fall within the boundaries of a circle. Try this, and I guarantee you, the decimal you get on the left-hand side will always, always, always be smaller than the decimal that you get on the right-hand side. You could show this for all of the angles from 1 to 360.
Are we gonna do things like this, like from now on in like our tests and stuff?
What?
In our like next test, is a question like this? Are there gonna be like questions like this?
I'm gonna go with sure. Yeah, why not?
Okay.
Are there any other questions about this second one, this much more difficult relationship?
To finish the equation, would you need to know like the actual equation of cosine, or is that not needed?
There is one property of cosine that you can use and exploit in order to get the answer here, and that property is the fact that sine and cosine will always return values which are less than 1. So this will always be 1 minus a number which is less than 1, which guarantees this is always positive. This will always be root 2 times a fraction, but the fractions that these are allowed to be will always be less than this object, which is about 1/60th. To move forward from here, you need to use special properties from pre-cal called trig identities. And I guess I might as well talk a little bit about them right now. For you guys at this level of mathematics that you're at right now, sine, cosine, and tangent are really only used for one thing and one thing only. What do we use sine, cosine, and tangent for?
Solve for the angles and sides of triangles.
Yeah,
Mainly
so you only
triangles.
So you only use the trigonometric identities when you are literally doing trigonometry for a triangle. However, you should know and be forewarned that sine, cosine, and tangent live rich, full lives outside of just triangle trigonometry. Let me show you the big two cases where you will see them use that. They are still trig functions, but this use of them isn't necessarily about physical triangles. Sorry, I want to pull up a couple different things to show you guys, not just one thing. Okay. So thing number one that you should be, oh, nope, not that one, this one. Thing number one that you should be warned about is that the trigonometric functions don't just calculate sides and angles. They are also codependent on one another in a way that is predictable and usable. So when you guys get to pre-cal year after next, a thing that you will be doing with these trigonometric objects is not just using them to solve for sides and lengths, but using them to relate directly to one another. And every single one of these properties that you can see on this trigonometric identity sheet is a true useful feature of these trig functions. That if you plug variables into them, you can relate them directly to each other in specific useful ways. And if you wanted to actually finish that relationship I started today, you would have to look at something like this in order to establish these length relationships for sure. You would have to do some fancy manipulation to take the square root of 1 minus cosine and turn it into something else that we could compare to the right-hand side more directly. Is that first part okay?
Mm-hmm.
Here's the other wild thing that sine and cosine are going to be used for as you guys move forward through math and science. They're graphs. If you graph sine and a cosine, and you could try this in Desmos right now, you just go to desmos.com, type in y is equal to sine of x or y is equal to cosine of x, or heck, try both of them at the same time. If you graph sine or cosine, it actually gives you back a wave. Because as you have sine and cosine process higher and higher and higher angles, it can only ever return back a number between 0 and 1, And as it oscillates through its potential output values, it produces this nice, clean, smooth motion, which we refer to as sinusoidal motion or cosinusoidal motion. And so if you're doing some sort of science which involves the modeling of waves, either literal waves like on the ocean or the surface of any body of liquid, or sound is a wave, light is a wave, all of these other scientific contexts in which we are considering waves or wave-like motion, we use sine and cosine to model those things because mathematically it is the perfect object to replicate how a wave behaves in space and time. Sine and cosine live very rich lives outside of just triangles. That's just kind of the first place where we figured out how to use them. And then as mankind went on since the ancient Greeks 2,000-ish years ago inventing sine and cosine, we found a lot more applications where sine and cosine are devastatingly useful. Nonetheless, you'll see all of that again in 2 years in pre-cal. So that's it for today's warm-up. Like I said, this week we'll be turning in all of last week's and all of this week's warm-ups together at the same time. This week we'll just be doing sections 3 and 4 starting tomorrow. And in case you are interested, the OWS for the entire rest of the school year is up in case you want to plan out your next few weeks accordingly. If you're What? You want attention? So today, if you're already done with the 10.2 homework, if it's already uploaded, you can head out and have a nice day. Otherwise, feel free to hang out and work on the 10.2 homework until it's done. It's due tonight. And if you have any questions, I would be more than glad to work them out on the webcam. And as soon as I'm done playing with this cat. Any questions out there?
Well, Mr. Officer, I turned it in. So
yeah, like always, if you've turned it in, once you've turned it in, feel free to roll out. You've earned it. Have a nice day. Go eat lunch early. And I'll see you tomorrow for a lecture. Tomorrow we're talking about secants.
Yeah, see you, Mr. Robinson.
Peace. Meow. There you go. Ooh, tiny cats. Alrighty, let me see how many people already uploaded the homework. I got 5 people who already turned it in, so 5 of y'all are free to go. Everybody else who's still here, do y'all have any questions on the current assignment?
I'm almost done. I'm on the last page.
Tight. Yeah, I think this one's pretty straightforward. We don't get to any fancy problem solving stuff until I think about section 4 is where we go over the first hard idea. For the most part, this section is just like either use the arc length formula or use it backwards, right? It's either just manipulate it forwards or backwards. Oh yeah, and I'm gonna turn the oven on for that sourdough. Mostly because if you don't know, you like cook a sourdough in the oven, but also inside of an iron pot, and it takes forever for the iron pot to preheat. Oh, by the way, did I already tell this group about stupid Minecraft graduation?
Yeah.
Oh, okay.
Yeah, how was it?
It hasn't happened yet. It's on Friday. But I figure on Friday, since I'll be attending it on my desktop anyway, which has like a real video card on it, I'll just like snip it, you know, like I'll just record the 15 minutes before they call my name. And if I can get like a good video capture of it, I'll post it on Classroom of some person in Minecraft reading out my name and degree in Minecraft.
Earlier in the Duna, when we were trying to find the arc, why couldn't we just say it was 70? Because like that was the angle.
That's the arc measure, not the arc length.
Oh.
Arc measure is the angle that is made by the arc, but the arc length, so the arc measure is this angle. The arc length, the length from here to here, also depends on the radius, and that's why we have the arc length equation, which comes in two forms. Is that okay?
Yeah.
And like I said, I'm just chilling here in my kitchen, so if y'all have any questions, I'd be glad to work them out. I think the homework's mostly self-explanatory though, so I understand if there aren't that many.
Mr. Robinson, I have a question.
Yes.
For on page 12, number 1.
On page 12, number 1. Yes. What about it?
I'd want to know how to solve it out.
Oh, so DE being written that way, it's just asking for the arc length. So what's the arc measure of arc DE?
120.
Yeah, so you just take all of that and then feed all of that to the arc length equation. So S is equal to theta over 180 times pi times r. So in that case of 12, page 12, question 1, this one is basically plug and chug. So that's 120 degrees of arc measure. And there's actually a word for that when you talk about how the two radii meet at the center of the circle to form that angle, we say that it's subtended by an angle of 120 degrees. You don't need to know that. I just think it's a good word. Anyway, 120 over 80 times pi, and then what was the radius of the circle?
2.
And then that's where the units here come from. And then the rest is just processing. So 120 over 180, we want to get an exact answer. So that'll simplify to 12 over 18. What's 12 times 2?
24.
Yeah, so it's 24 over 18 is the fraction that we want to simplify down. So we could just bust this down to make it a little bit simpler. So that's the same as 12 over 9. Then we could divide 3's out of those. So that's 4 over 3. So then that is to say that this is equal to 4 pi over 3 meters, which if you take that and you turn it into a decimal, since pi divided by 3 is just a little bit more than 1, right? Because pi is just a little bit more than 3. This ends up being about 4.19 meters.
Okay, thank you.
Is that okay?
Yeah.
Cool.
See you tomorrow, Mr. Robinson. I'm done.
Oh, you got it uploaded?
Yeah.
Cool. Have a nice day. See you
You
tomorrow.
too.
Being downstairs in the kitchen is super weird. Oh, also, my earbuds are dying because I'm using my wireless one so that I could move around in the kitchen while teaching. Give me 1 second. I'm gonna switch headphones. Which means I need to turn Bluetooth on. Devices. I'm gonna mute everything for a second just because I don't want the Zoom to freak out while I'm switching headphones and stuff. Mute. Is it raining outside right now? It stopped like 15 minutes ago where I live.
It's still raining in
Yeah,
Pasadena.
it's still raining.
Oh yeah, it's still raining in Pasadena?
Yeah.
Mhm.
Huh, maybe I'll run that way. See if I can run all the way to where it starts raining. Thank you for ripping me up, Oogie. I was planning on going for a longer run today. I might run all the way from my house to like Old Town Pasadena, like Dodger Stadium to Old Town Pasadena. I think that's like 6 or 7 miles one way. No, it's 6 miles, 5.5 miles one way. So it'll be like 11 round trip. Okay, the time is 12:25. So if there's no other questions out there, I'm gonna shut the stream down and stuff, and then tomorrow we have lecture. Are there any last minute questions out there before we head off for the day?
No, I'm good.
Okay, you all have a nice day. If you have any leftover homework questions, just holler at me tomorrow while we're doing the warm-up, and I'll see you all on Tuesday.
Okay.
Peace.
Bye.